your page. You've got the notes, 1.2, rates of change. You're going to see the abbreviation AROC, A-R-O-C, and that represents average rate of change. And up there at the very top, you've got a little blank to fill in. And it says the average rate of change between any 2 points on a graph is the slope through those points. So in this little box right here, just to show you kind of how you would find an average rate of change, let's say, of a parabola here. Here is the formula that you can plug into. I'm going to show you different ways of going about this so you don't feel like you have to plug into the formula every single time, because that can be tedious. Sometimes there's an easier route. Sometimes you're given 2 points and you just have to plug in the old slope formula, or in pre-cal, as we refer to it, average rate of change. So here are the steps. You're going to find the y values of the function for the given interval. That's going to have to be your first step, because look at the formula. On top, you've got the change of y. You might actually see me write that as delta y. Maybe your Algebra 2 teacher also wrote that as delta y, a little triangle y. That's the change in the y values. That just means what's the difference. We subtract them over the change in the x values. So first thing you're going to have to do is find your y values, and then you're going to need to find the slope between the 2 points. That's what we're going to practice first and foremost with example 1. The directions there say find the average rate of change on the given intervals. So we're kind of going to have to get used to the way things are written and how things look so we know exactly what we're supposed to do. For A, we have this function negative x cubed plus 3x. And we're supposed to find the average rate of change on the interval from x equals negative 2. So that's going to be like your x1 value, all the way over, sweeping to the right, all the way over to our second x value being negative 1. This is not an ordered pair. This is an interval of x values. We're going to find on average what the slope is doing from negative 2 to negative 1. So the very first thing you're going to have to do is say, okay, well, if I plug in negative 2, that first x value, what is f of negative 2? We're going to have to figure that out. So that's going to be negative times negative 2 to the third plus 3 times negative 2. Let's do PEMDAS. What is negative 2 times itself times itself? That's negative 8, and then we're going to have to change the sign on that, so that's going to be positive 8. And then 3 times negative 2 is negative 6. And 8 take away 6 is 2. That's going to be what you're going to treat in second as your y1 value. I plugged in my x1 value, that's my input. I got out my y1 value of 2, that's the output. So you can think of it as, now I've got an ordered pair. I have negative 2, 2, and now I'm going to see what happens when I plug in negative 1. Take a second and see if you are confident in plugging in negative 1 into the function. And you should have an output value, a y2 value of negative 2. Now and only now are we able to figure out what is the average rate of change on this interval, because we have 2 input values, 2 output values. You can follow that formula then at the top of the page, which says average rate of change is your y2 value, negative 2, take away your y1 value of 2, over your x2 value, the second thing that you plugged in, your second input, negative 1, subtract the very first input value, which was negative 2. So that's going to change to, instead of minus a negative 2, that just changes to plus 2. Negative 2 take away 2 is negative 4. Negative 1 plus 2 is 1. and we finally arrive at our answer. The average rate of change on that interval is 4 or 4 over 1. That's the average slope of that interval. In just a minute, you'll kind of get to put pictures to all of this math, and it'll hopefully gel a little bit better for you. Did I mess up? Yes, it is -4. Thank you. Some of you are looking back here. You guys be brave, be bold. I'm never going to be offended. When I make a mistake, let me know. That's -4. Thank you. I make mistakes all the time. All right, B. Same concept. Here's the function. We have input values of 1 and 4. Let's see what the average rate of change is for this function. We don't even know what the graph looks like, but we can figure out the average rate of change. So I'm going to be quiet for a second, and I want you to just kind of work on this one and see if you understand the task. Plug in 1, see what you get. Plug in 4, see what you get. Then find the slope, or the average rate of change, rather. We got some nice fractions going on in this problem, so take your time. I'm going to zoom in just a tad. We're going to need some common denominators there for your y values. It's going to be 14ths. So I went ahead and just changed those into their common denominators so that I could subtract on the top. I want to show you a little trick right here that you may not know when you have a fraction divided by another number. That's the same thing as this. These are the same thing. The 3's cancel and we end up with 1/14. Now, I want you to look at this and ask me any questions that you may have. Right here, so I saw that my y1 and my y2, the denominators were 7 and 2. So I knew I needed to switch those into a common denominator of 14. 7 times 2 is 14. So if I multiply the bottom by 2 to get 14, I have to multiply the top by 2. What you do to the bottom, you do to the top just to keep it equivalent. That's how I got the 4/14. I'm getting it from this 2/7. The 7/14 comes from the 1/2. And then again, I want you guys to know these tricks, especially because, again, you're not going to get to use a calculator on the test, but I want you to be able to move quickly and confidently through the exam. So 3/14 divided by 3 is the same thing as 3 over 14 times 3. So you can just quickly cancel out the 3's, and that's 1/14. So the average rate of change can totally be a fraction. I mean, that's like rise over run. Now you're about to see how it can be a lot easier. There's not going to be a whole lot of work to do on example 2. Here's a picture of a function, and it says, the graph of g of x is shown below. Let me zoom out so you can see it all there. Find the average rate of change of g of x over the interval -1 to 3. So I want you to put a point on the graph where x is -1, and it's right here. That's where x is -1. All the way to 3. So here's what's kind of crazy. Check this out. This is going to be important on the next page. Right here, the slope is like positive, and then it's like leveling off, and then it turns to negative, and then it's leveling off, and it turns to positive. So the slope is changing a lot from -1 to 3. We're trying to figure out, on average, what is the slope doing? What's the on average rate of change? So here's how easy it is, okay? Draw a line between those 2 points, bless you, and it's just the slope of that line. That's it. It's rise over run. You just have to count. How many up do you need to go to get from one point to the other? What's the vertical change? 4. What's the horizontal change? 4. So check this out. The average rate of change, the change in your y value over the change in your x value, that's that delta y over delta x I was telling you. To me, that's easier than writing y2 minus y1 over x2 minus x1. That's just a change of, well, we had to go up 4 and we had to go right 4. So guess what? The average rate of change and all of that craziness of it going up, leveling off, going down, leveling off, going back up, on average, the rate of change is 1 over that interval. So it doesn't always have to be as intense as plugging into a formula. You are more than welcome to come up with these ordered pairs and plug them into a formula. Plug and chug. But I think this is a little easier on the brain. Okay. I didn't have you grab a calculator today, so I'll help you out with this part. You also need to be able to figure out the average rate of change from a table. So far, you've learned, when given a function, how to plug in and find the rate of change. That was example 1, A and B. How to find the average rate of change from a graph on an interval. And now we're switching gears and we're going to look at a table. The table above lists the life expectancy of U.S. females born in a given year. So you've got the year and the average life expectancy. Find the average rate of change in the life expectancy of U.S. females born from 1850. Think of that as an ordered pair, to 2000. Think of that as an ordered pair. So we want to know, on average, what's happening to the life expectancy as the years go by from 1850 all the way to the year 2000. So the concept remains the same. We need to find the change in the y values. You think that's going to be year or age? Yep, age. It's usually like the bottom of the table, right? That'd be your output. So the change, the average rate of change, is going to be the change in the y values. If you're a person who likes to label and stay really organized, 1850, you could think of that as your x1 value, and the year 2000 could be your x2 value. 46.10 could be your y1 value, and 81.83 could be your y2 value. Like I said, I know you don't have a calculator, so I'll help you out with the subtraction here in just a second in the division, but that's going to equate to, the formula at the top of the page would tell me that I need to do 81.83 minus 46.10. That's the change in the y values, delta y, over 2000 minus 1850. The really cool thing is this: the order that you subtract does not matter. You could have done 46.1 minus 81.83 over 1850 minus 2000, and you're going to get the same exact answer. So don't feel like, how do I know which one is x2? How do I know to start with that? It doesn't matter. So here's what you're going to get when you crunch the numbers. You're going to get 35.73 over 150. Which is 0.238. Anytime you're working on a calculator section of the exam, which this definitely would be, always round out to the nearest thousandths, the third decimal place. Now I want to add some context to this. So what did we just figure out? Yes, the average rate of change, but in context as far as like years and age and... Yep, it's the increase per year of the life expectancy. On average, the life expectancy is increasing by 0.238 per year. You can put, this is really weird, but age, years per year. That's how much your age, your life expectancy, and if that makes more sense to you, that's life expectancy, is increasing by that much per year on average. So on page 1, we're finding the average rate of change on kind of a larger interval, like a big span of x values. Well, there's this concept called instantaneous rate of change. Let's read what it says here. The idea of instantaneous rate of change is equivalent to finding the rate of change of a function like at a single point. Not really over an interval, but what is the slope of that point? This concept is developed formally and used in calculus, but we can approximate the rate of change at a point by using the average rate of change over small intervals. And I'm going to help you out with this one as well. So your idea is just to keep the big picture. I will help you crunch the numbers. This would definitely be a calculator problem. A ball is thrown vertically into the air. When you read something like this, I don't want you in your head to say, for 0, alligator mouth T, alligator mouth 5. I want you to understand that means between 0 and 5 seconds of time. The height of the ball is modeled by this function. From 0 to 5 seconds, here's the function, where h is measured in meters and t is measured in seconds. Find the average rate of change in the height of the ball over the following intervals. So we know the ball is going to do this. It's going to go up, it's going to come down. So it's quadratic. And let's say I wanted to know exactly what the slope of the ball is doing right here at this one single point. What we can do is we can just get a teeny tiny little interval and kind of see what it's doing there. And that's the goal, is for you to see if we start with a broader interval from 1 second to 1.1, and then we go smaller, 1 to 1.01, and then even smaller, 1 to 1.001, and then another small interval, like what's happening as we squeeze that interval and make it smaller and smaller and smaller. Let's see what happens. So on part A, what you would need to do is you would need to plug in, don't worry, we're not going to have to do this, you would have to find h of 1.1 and subtract h of 1. Those are your output values. That's what we did. The very first mathy thing we did today is we plugged in a couple of things to a function. So we would have to figure out what those are and subtract them over the change in x's, which would just be the 1.1 minus 1. I'm going to go ahead and tell you right now, you would find that the average rate of change in 1/10 of a second is 14.71 meters per second. 14.71 meters per second. And that is rounded out to the thousandths. It just was 14.710. You could do this if you had a calculator. That's the expectation. Well, let's see if we make the interval even more small. So now it's just 1/100th of a second difference. Let's see what the average rate of change is in 1/100th of a second. So again, the process would be to grab your calculator and figure out what h of 1.01 is minus what h of 1 is. That's your change in your y's over 1.01 minus 1. And you crunch all those numbers, and here's what you would find. It's a little bit different of an answer. It's 15.151 meters per second. So the slope is steeper. You guys have any questions? Okay, then we're moving right along. Here, you can probably guess, okay, so I would have to grab my calculator and plug in 1.001 to this function up here that I've highlighted. That would be kind of tedious, right? But I have to plug that in, see what I get. Plug in 1, see what I get, which luckily we've already done 2 times before, so that would be easy. And then we would do 1.001 minus. And what we would come up with is, on average, in that 1,000th of a second, their average rate of change is 15.195 meters per second. Very close to what we got here, but it's just becoming a little bit more accurate. We're fine-tuning it. We're closing the interval in and trying to figure out what is the slope at one single point. In other words, a teeny tiny little interval. And then the last one down here, same exact process. We would have to find h of 1 this time and subtract h of 0.999. It's still 1,000th of a second difference over 1 minus 0.999. And what you would end up there with is 15.2049. 15 point, let's do 205 meters per second. Still very, very close to what we've been getting. So here is the big question, because I didn't want you to get all caught up in the calculating part of this. I just want you to see what's happening as we close the interval in. Based on what you've just seen, what do you think, what would be a good estimation for the true rate of change at exactly 1 second? Well, we could figure that out. We could plug in 1 second, right, up here. But what do you think it's going to be close to? It's going to be close to, yeah, C and D, right? Because these intervals are really, really, really close to just a single point in time. The interval is tiny. And so you can put the true rate of change is close to what we got on D. And then I just want you to know you could actually find that by plugging in 1. And you sure enough would get 15.2, bless you, meters per second, which is really close to what we got for D. So when you close your intervals in, it just helps you get a good estimation of an instantaneous rate of change. Now that's very tedious. So let's see, maybe we have another option in pre-calc for figuring out instantaneous rates of change that doesn't require a lot of work. Let's keep reading underneath that line. The rate of change of a function at a particular point is the rate that the y values change if the x values changed at that point. This concept is what we call instantaneous rate of change later on in calculus. Now, we can't find the rate of change at a particular point in pre-cal, but we can do one of two things. We can estimate what we just did up there. We can estimate the rate of change at a point by finding the average rate of change over a very small interval. That's one option, and it's pretty tedious. Or, what you're probably going to prefer, unless you're forced into a situation like this where you just have no choice, you've got to do it, you're probably going to prefer option 2, which is to estimate rates of change. We're always just estimating. It's not until calculus that you can get exact with this, but we can estimate rates of change at 2 different points by estimating individual rates of change using the concept of a tangent line. And I'll show you more about that on the next page. But what's down there at the bottom of your page is hugely important. When we discuss rate of change, we are essentially discussing the slope, and I think most of you understand that by now. If the graph has a positive rate of change, a positive slope, then the graph is increasing. That's kind of like a no duh, right? If the graph has a negative rate of change, a negative slope, then the graph is decreasing. On Friday, we just practiced kind of eyeballing where graphs were increasing and decreasing, and most of you don't have any trouble with that. But I want you to put that together now with the idea of rate of change. If rate of change is increasing, the graph is increasing. Excuse me, if the rate of change is positive. And if the rate of change is negative, the graph is decreasing. Now turn the page. And eventually, when I quiz you on this stuff, you're going to have some situations like this where it says, for each scenario below, determine whether the two quantities typically have a positive rate of change or a negative rate of change. Like, do they have a positive relationship or a negative relationship? So let's look at a child's age versus the height. Okay, here's how I do these. This is really how I do this. As age goes up, what happens to a child's height? Height goes up. If they're both doing the same thing, if they're both going up or both going down, then they have a positive relationship. That's it. Let's look at the next one. A golfer's skill level versus the golfer's score. So as skill level goes up, as you get better and better at golf, what happens to your score in golf? It goes down. Score goes down. If one variable is increasing while the other one is decreasing, that has a negative relationship. It's got a negative rate of change. And then don't overthink C. I read some teachers had kind of had some trouble with this, and I think they were just overthinking it. The height from the ground of a coin dropped off of a really tall building versus the speed of the coin as it falls. You don't have to think about physics or gravity slowing, nothing like that. What happens as the height from ground, if we're dropping it, the height from the ground is decreasing. It's getting closer and closer and closer to the ground. Well, what's going to happen to the speed? The speed, it's going to get faster and faster and faster. That's it. Don't overthink this one. Does that have a positive or negative rate of change? Negative. Why? One's going up, the other's going down. That's it. That's all you have to think about. So I hope those are easy for you when you have a little scenario. Now I get to talk to you about this tangent line stuff, and this is hugely important. Estimating rates of change at a point. The graph of f is shown above along with the line tangent to f. I'm not really talking about like the sine, cosine, tangent right now. So even though you might have heard that word, this is what a tangent line looks like, okay? It just kind of like comes in and it scathes the graph at one point. So that would be the line tangent to this curvy function. When x equals -4. So right here at this point, that's where x is -4, and this is the line tangent to the graph at that point. So you're just kind of getting used to some vocabulary. In calculus, we're going to learn that the slope of the tangent line, the slope of that line is the true rate of change at that point. So while we can't find the slope in AP Pre-Cal, we can sketch the tangent line and estimate it, okay? So here's what we're going to do. Example 6 says estimate the rate of change at x equals -4 using the slope of the line, tangent to f, at x equals -4. All you have to do, it's already sketched for you, is find the slope of that line. Now, we're going to have to estimate. That's the key word here. Because if you're trying to find the slope of a line, what you need is two really clear points. And I like this one up here, this -2, 5. where it's going right through what I feel is negative 2, 5. And then we're just going to kind of have to estimate a little bit on the slope. Does it have a positive or a negative slope? It's got a positive slope. So big picture, we have a positive average rate of change here. And then, I don't know, this kind of looks okay. It's not super duper clear, that negative 5, 1. It's not really going through negative 5, 1, but we can estimate. So what's the rise over run? From this point to this point. 4/3 would be a really good estimate. The teacher that made these notes, he put 3/2, but it's just an estimation. So we can put that the slope is positive for sure. I want you to note that. And somewhere around, we said 4/3 because the rise over run is positive 4/3. So about 4/3. Now this is going to be challenging for some of you. Example 7 says sketch the lines or sketch the tangent lines at the 5 points indicated on the graph. Okay, so these 5 points that they have, we're going to be sketching tangent lines. I'm going to use a ruler. You don't have to, but I just want to make sure my notes are nice and pretty and nice and neat for you. But if we're trying to sketch a line tangent to this point right here, I'm just going to butt my ruler right up against that point because I'm really trying to just touch the function, the graph, one time. I'm just trying to see, like, it's barely going to touch. It's kind of challenging, so those of you that like to be exact, this is going to drive you crazy. But it's going to be something like that. Does that have a positive or negative rate of change right there? Negative. Okay? Now we're going to go down to this dot right here. And I'm going to try and, to the best of my ability, I'm going to try and draw a tangent line, which kind of-ish means that it only touches the graph once, but sometimes it might touch it more than once. So I'm just trying to see the main point here. It's arbitrary, it doesn't matter. I just don't feel like going all the way across the page because then the picture would be really busy. So I just kind of draw a little segment there so I can see it just come in contact with the graph at that single point and then leave. Pause. Is this, at this point, is there a positive or negative rate of change? Negative. But is it less steep? Listen really closely. Is it less steep or more steep than the orange one that I drew? It's less steep. So this has an increasing right now, went from pretty negative, pretty steep in the negative direction to less steep in the negative direction. So it has just increased its rate of change. Barely, but the rate of change, the slope, has increased from here to here. Now I'm going to keep going. This bottom one's really easy. You just need a tangent line. Down there, it's going to be horizontal. What's the slope of that line? 0. Horizontal lines have a slope of 0. So now it's even less steep. As a matter of fact, it's a slope of 0. And then if I continue in that right direction, in that right-handed direction, now the rate of change has changed to positive. Now it's going up. It's increasing. The rate of change is positive. And then the very last one up here, this point here at 5, I don't know, 3.5 or something, that one's going to be positive, but it's going to be even more steep. It's very important that you're understanding when I pause and I say, talk about the steepness here. Because here's what happened from orange to purple to green to pink to turquoise. I want you all to look at the board. Just take a pause and check this out. From orange to purple to green to pink to turquoise. Watch my pen. Orange, purple, green, pink, turquoise. That rate of change over that interval, was the rate of change, was the slope increasing or decreasing that entire time? Watch my pen. Is the slope increasing or decreasing? It's increasing that entire time. It goes from very, very negative to less negative to 0 to positive to really positive. So on that entire interval of concave up, that rate of change, that average rate of change was increasing. Very important for you to understand that. The wording can be super confusing, but if you see it in a picture, I'm hoping that that helps. So example 7, you can just put a check mark there. Yes, ma'am. Well, we haven't really been asked a question about this yet, but I just want you to know that, like, there are two separate schools of thought. If I just ask you, hey, look at the orange line, is the rate of change at the single point increasing or decreasing? You would say decreasing because it's got a negative slope. But over time, the average rate of change over this interval of x values is increasing. Okay? So it's different than the concept of instantaneous. It's over an interval. Okay, now let's answer example 8 before we turn the page. Does the graph appear to have a greater rate of change at x equals 4 or x equals 5? And I kind of already answered that for you. Which one of these has a greater slope? X equals 4 or x equals 5? 5 has the steeper slope, so its rate of change is greater. And on the explain part, you can just put it's steeper. The tangent line is steeper at x equals 5. So we've really got some new concepts for our brain, and it's about to get even more challenging. Turn the page. This is what Addison was asking, or kind of how I answered Addison. There are two different ways that you have to think about this. If the slope is positive, the graph is increasing. I promise you aren't going to have any trouble with that. If the slope is negative, the graph is decreasing. You're not going to have any trouble with that. Here's where things get interesting, and you're going to have to practice over and over and over until it just clicks. If the rate of change is increasing, like what I just showed you when I paused and I said, everybody look, from orange to purple to green to pink to blue, the rate of change is increasing. That means the graph is concave up. And that's what this says right here. The graph is concave up. When the slope is changing in a positive direction over time, that creates a scoop, a concave up, a smiley face. If the rate of change is decreasing on an interval, so the slope is slowly turning more and more negative, that's going to make a frowny face. The graph is going to be concave down. If you're a memorizer, memorize these. But you're going to find that you have an easier time in a course like this when you're not just a memorizer and you truly understand the concept. So I can throw any sort of critical thinking question at you and you really understand it instead of just regurgitating this little table. So let's kind of use this knowledge on this graph of f. Sorry, that's cut off a little bit there. But it says, the graph of f is shown above. Complete the blanks to correctly describe the graph and its rate of change. So it's kind of like a fill in the blank and your options are right underneath. The graph. Look at the graph itself. Is the graph increasing or decreasing? That's easy. The graph is definitely increasing. Just the graph. When you read it left to right, it's going up. Is it concave up or down? It's concave down. It's got more of like a frowny face shape to it. So those are Friday's concepts. It's concave down because the rate of change is blank, positive or negative. Well, what's the rate of change at any Check this out. If you want to draw some tangent lines, you can. What's the rate of change? At any point, it's positive. The slope of any tangent line to this graph, that slope is going to be positive. So the slope of the graph is positive, this entire graph. But what is the rate of change doing? Watch my pen. It starts kind of like steep, and then it gets less steep and less steep and less steep and less steep. So is that slope increasing or decreasing? That slope is decreasing. That rate of change is decreasing. That little AP tip down there at the bottom, just be careful when you're answering questions about graphical behavior. The wording, is it asking about the graph or the rate of change? And that's where people get confused. Just pay attention to the actual question about, is it the graph? Do they want to know if that's increasing or decreasing, like this first blank? Or do they want to know if the rate of change is increasing or decreasing, like the last blank? Those can be vastly different. Turn the page. This last page I'm hoping is going to be pretty gentle, kind of putting all of these concepts together. For each of the graphs, circle the correct description for the behavior. Okay, I'm not really a fan of this, but it's just so easy that people are going to overthink this. You see this graph right here? Is it above or below the x-axis? It is, all of that graph is above the x-axis. That means the graph is positive. Let's just go ahead and go down to graph G and answer the same question. This entire graph, the graph of G, is it positive or negative? Negative, and why are you saying that? Because it's below the x-axis. And then what about the graph of H? It's positive. Okay. That's just weird. Like, even other AP teachers were kind of uncomfortable with that. But whatever. Okay. That's the rest of the stuff that I really want to focus on. Up here, graph of F. Is the graph increasing or decreasing? It's decreasing. It's going from way up high and then it's scooping down. So the graph is decreasing. What about the rate of change of F? I'm going to stick right up here. I'm going to answer this question. The rate of change, the slope. It is increasing. Is it positive or negative? At any point, the tangent line is going to have a negative slope, right? So the rate of change, the slope of the graph is negative. And then some of you already answered the last one, which I think is the hardest one. Once your brain grabs a hold of this, it's going to be really easy for you. But as I move through here, the slope of those tangent lines is becoming less, it was really negative, and it's becoming less and less negative. So is the slope increasing or decreasing? It's increasing. Increasing. You want to know a cheater way? This is super easy. That's concave up. And anytime a graph is concave up, check this out. The rate of change is going to be increasing every single time. So look at G. I'm going to go out of order. Is this concave up or down? It's concave down, and most of you can know that right away. And any time a graph is concave down, the rate of change is what? Increasing or decreasing? It's decreasing. It's getting less and less positive. Okay, overall though, is the graph of G increasing or decreasing? Increasing. And what about the rate of change the entire time? What's the slope? It's all positive. At any given point, that slope of the tangent line is going to be positive. Look at H. Concave up or down? Concave down. If it's concave down, what's the rate of change going to be doing? It's going to be decreasing. And if you're still wondering why, look at my pen. I start out, I get more and more and more negative. That slope is decreasing. The graph itself, the graph of H, big picture, increasing or decreasing? It's decreasing as you move from left to right. It's going in the downward direction. And what about the slope the entire time? What's the slope of all those tangent lines? It's negative. Very good.